In the video where I went over the periodic table, I mentioned that I would go further in depth on the difference between ionic compounds and covalent compounds. So this is me fulfilling that promise. So I'm going to set up a little table. Ionic and covalent. So as mentioned previously, ionic compounds are between metals and nonmetals, and covalent compounds are only between nonmetals, so they're between two or more nonmetals. In an ionic compound, electrons are thought as being transferred, and I'll explain what that means in a moment. In covalent compounds, electrons are shared. So what do I mean? Well, I used the example previously of lithium chloride, LiCl. And I said that lithium forms a positive ion by losing an electron, and it gives that electron to chlorine to form a negative ion. So we describe that as lithium transferring its electron to chlorine. Whereas in a covalent molecule, let's say water for instance, water is one oxygen bonded to two hydrogens. So in covalent molecules, we draw these lines that we refer to as bonds. And what those bonds are is each bond represents two electrons. One contributed by each of the atoms involved in the bond. And we think of those electrons as being shared between the two. So it's like almost like they're holding hands, and they're just keeping those electrons there in that handshake, held between the two of them. So that's what it means to have electrons being shared between covalent bonds. So now, when these form structures, these will form, ionic compounds will form ions and ionic lattices. What does that mean? Well, obviously they form ions, right? But these don't just form as often as a single lithium ion and a single chlorine ion. What you'll often get is you'll get a lithium ion next to chlorine, then another lithium, then another chlorine, then another lithium, then another chlorine, going down, chlorine, lithium, chlorine, lithium. And we can keep going, and they can alternate like this, right? And we can keep going in 3 dimensions, and this is what's referred to as a crystalline lattice. So it's an ordered, repeating, sequential solid formed from these ions. And the ions have a tendency to form this type of a lattice, right? So they form as just this ionic lattice, whereas even in an entire molecule, so even when you, or not molecule, when you get even like a large structure, covalent molecules tend to form as single molecules. I mean, there are ways to get covalent molecules into crystals, but that's not how they naturally form. So, or even if they do form into crystals, they form as single molecules that just happen to be near each other, right? So all these water molecules are still, that's a hydrogen, sorry. They're still individual molecules that just happen to be near each other, but not actually forming ionic bonds with each other. And last thing, the difference between these that I want to discuss are that ionic compounds are good conductors of electricity. Are good conductors. And covalent compounds are not good conductors, because in order to conduct electricity, you need the presence of ions. Now you might say to yourself, wait a second, I've seen plenty of examples in movies, on television, of electronics being put into bodies of water and electrocuting things. And you can look at plenty of electronic equipment, and they will have warnings to not put them in water. But you just said covalent water is a covalent molecule, and that's not a good conductor of electricity. So what's going on? Water by itself is not a good conductor of electricity because it doesn't have any ions. However, none of the water that exists around us in our daily lives is actually just pure water. It all has trace impurities, trace amounts of different types of impurities. And these impurities are in the form of ions. So all water around us in our daily lives actually has some ions in it, and it's those ions that help conduct electricity. So it's not actually, so if you actually have a pure body of water. It's literally nothing but H2O molecules. So that's actually not going to be a good conductor of electricity because of the lack of ions. But once you get some ionic impurities in there, that's when water conducts electricity. And the last thing I want to talk about for this is something called polyatomic ions, because these are kind of a hybrid of the two. Now, on Blackboard, I have a list of common polyatomics that I posted, and so for the common polyatomic ions, you'll want to memorize those because you'll be you can be expected to know those. So you'll want to know their name, their formula, and their charge. Right? So I'll just use one for an example. So let's say we have NO3 minus. This is nitrate. Okay. So that the name of it is nitrate. Its formula is NO3, and its charge is -1. So what is a polyatomic ion? Well, if we were to show just the general structural formula of it, this is a nitrogen covalently bonded to 3 oxygens. Right? So within the polyatomic ion itself, you have covalent bonds between these nonmetals in the polyatomic. So in polyatomics, they're always going to be made up of nonmetals. However, this entire thing as a whole has a charge. In this case, -1. They're not always -1, so that's why you'll want to remember the charges for your common polyatomics. But for nitrate, it is, right? So this entire covalently bonded molecule collectively has a -1 charge. And so it collectively can act as an ion. So it can bond with a metal, for instance. Let's say NaNO3. So Na, sodium, right, that's a metal, and that has a +1 charge. This has a -1 charge, so they can actually form. So this is an ionic compound, but it has this covalent. So it's an ionic compound because it has a metal and these nonmetals, right? That is the definition of ionic. However, so ionic compounds can, well, obviously, as I've mentioned before, can break up into their ions. The ion we get from sodium is Na+, and from the nonmetals, they stay together as their polyatomic ion. So it'd be NO3-. These covalent bonds within the polyatomic do not break apart, no matter what.